The goal of this video is to explore through an example what happens in the case when our eigenvalues are complex numbers. So suppose we want to find the eigenvalues and corresponding eigenvectors of the 2 by 2 matrix, -4, -17, 2, 2. Recall that we first must find the characteristic polynomial. We want to find all values of lambda such that the determinant of lambda times the identity minus a is equal to 0. So we have lambda times the identity here minus our matrix A. And so we want to compute the determinant of the matrix lambda plus 4, 17, -2, lambda minus 2. The determinant, of course, will then be lambda plus 4 times lambda minus 2 plus 34. We multiply out and then complete the square to see that our eigenvalues will be the complex numbers -1 plus or minus 5i. All right, so we found our eigenvalues. Note that process is exactly the same, whether your eigenvalues are real or complex numbers. The interesting piece is going to come in finding those eigenvectors. So to find the corresponding eigenvectors, let's first consider the eigenvalue -1 plus 5i. And recall that to find the eigenvector, we need to solve the equation -1 plus 5i times the identity minus a x equals 0. Recall that the matrix A is -4, -17, 2, 2. And therefore, -1 plus 5i times the identity minus a simplifies to 3 plus 5i, 17, -2, -3 plus 5i. Now, the row reduction here is really unpleasant because of these complex numbers. So we want to come up with a different way to go about solving this system. The key observation is that since our lambda -1 plus 5i is an eigenvalue, then the system that we get, our lambda I minus ax equals 0, that system is guaranteed to have a non-trivial solution. All right, so I'm going to take this system to another slide to have a little more room to work. So here's our system that we know for certain has a non-trivial solution. And therefore, both of the equations that you see here determine the same relationship between x1 and x2. And either equation can be used to express one variable in terms of the other. So we're going to focus on that second equation. The second equation and solve. So we get minus 2x1 equals minus -3 plus 5i x2. So just subtract to the other side, divide both sides by -2, and we get a relationship between x1 and x2. So x1 is 1/2 times -3 plus 5i x2. Now note, we could have used either equation that we wanted to, but the key is that we want to keep the complex number in the numerator. Note we divided by the -2. So we do not want to divide by a complex number. Division of a complex number is just beyond the scope of what we're learning about in this course. So we always want to keep that complex number in the numerator. Okay, so x1 is 1/2 times -3 plus 5i x2. So now we're in the home stretch. If we let x2 be t, then we can write the eigenvectors for the eigenvalue -1 plus 5i as scalar multiples of vectors whose first component is 1/2 minus 3 plus 5i and whose second component is 1. And then, of course, since we're talking about scalar multiples, if we think about multiplying by 2, that's not going to hurt anything. So if we want to, we could also just write them as scalar multiples of -3 plus 5i, 2. Great, so these are the eigenvectors for our first eigenvalue, and now we know the process. So finally, let's consider our second eigenvalue, -1 minus 5i. Again, we need to solve the equation. -1 minus 5i times the identity minus a, all of that times x equals 0. Recall a is the matrix, -4, -17, 2, 2. And therefore, minus 1 minus 5i times the identity minus a equals 3 minus 5i, 17 minus 2 minus 3 minus 5i. So using row 1 of this equation, we have that 3 minus 5i x1 plus 17x2 equals 0. We want to keep that complex number in the numerator. So we would, to solve for x2, subtract to the other side and then divide. So x2 is 3 minus 5i x1 times negative 1/17. In that case, we would let x1 be our parameter, and our eigenvectors become scalar multiples of vectors whose first component is 1 and whose second component is negative 1/17, 3 minus 5i, or multiply through by that negative 17 and take your eigenvectors to be scalar multiples of negative 17 times 3 minus 5i. Now, that's the case where we focus on row 1 of our system. Just in case you're curious, if you had wanted to use row 2 instead, you could have done that. Row 2, the relationship tells us that minus 2x1 plus minus 3 minus 5i x2 equals 0. We solve for x1 to keep that complex number in the numerator. And then if we let x2 be t, our eigenvectors look like this. Great. Also in the slides is another example you can work through. Suppose A is the matrix 1, negative 2, 1, 3. Compute that determinant. You'll find your characteristic polynomial, and you'll see that your eigenvalues are 2 plus or minus I. For the eigenvalue 2 plus I, your eigenvectors are scalar multiples of negative 1 plus I, 1. And for lambda equals 2 minus I, your eigenvectors are scalar multiples of negative 1 minus I, 1. And the details of this solution are available in the slides that are posted on Blackboard. That's all for now.